recorded.
And hopefully there's audio. Brenna, can you hear?
Yeah, you're good.
Excellent. Thank you. Okay, welcome to our data mining class. For today, we're going to do several things. One thing is there's another printout up here up front where that's located in the GitHub repository for electronic people is in this project transfer learning inside of the topic 6 applications model zoo folder. There's a notes.pdf file in there. And we probably won't get through all of that today. We might not even get to it today. But that is the description of your next homework assignment. So you, after today, even if we don't talk about the full notes packet after today, you can definitely start the next homework assignment. We will talk about enough stuff today that you can start the next homework assignment. This is what that file looks like. Transfer learning on image data. You will be doing some, this link right here, doing some PyTorch and computer vision stuff for your next homework, trying to decide whether a picture is of a bee or of an ant. So that's one thing that we'll be doing today. The next thing that we will be doing today is on this model zoo set of notes. We will finish up this model zoo notes. There will be more models that we will be talking about next week. I'll have more sets of notes with different model types that we'll talk about next week, but we will finish up our discussion of everything in this notes packet definitely today. And the first thing that we will do, the administrative-ish thing that we will do, is we will talk about your midterm 2 exams. Everybody's now completed them, so we are able to talk about them now. So here's what the grade distribution looked like. Overall, I was very, very happy with the midterm 2 exams. If we compare them to the midterm 1 exam grade distribution, a lot of shifting to the right here. A lot of people really improving your scores on the midterm 2. So I'm very happy about that. So I've divided up the things for us to talk about into sort of 2 categories. Again, the category of things that were bad habits, sort of mistakes people made that did not result in points being taken off, and then mistakes that did result in points being off. These bad habits, again, are things that you will hopefully, as you get more practice, learn to correct yourself about these, not be in these bad habits. These are the sort of bad habits that, again, they won't get you points off on the final exam, but they might get you a not hiring decision on a technical interview at a company. So pronunciation-wise, the one thing that came up was actually a couple people did this. The Scripty X that the textbook uses to represent a data set. This is not a Greek letter. This is actually the letter X written in cursive. And this is what the Greek chi letter looks like when it's typeset, which also sort of looks like a Scripty X, but there is no Greek chi letter used in this class for anything. This is just a Scripty X. The textbook uses the script font for anything that is a set, and so our data set is that Scripty X. Some not technically correct language that a lot of people use that you really want to try to get out of your vocabulary, get out of your speaking habits I think I have 3 examples here. So again, I have an incorrect and a correct usage example for each of this type of language. This incorrect example up here, the in-sample error greater than the generalization error means that you're most likely overfitting. This is the definition of overfitting, and so it's not that you are most likely overfitting, it is that you are overfitting. If you're using a phrase like most likely or reliably or tends to be or any of this sort of equivocating language, then you should only use that if it's not 100% guaranteed to be true, following immediately from a definition. So a correct way to use the phrase most likely would be something like a large VC dimension compared to the number of data points means we are most likely overfitting. It doesn't guarantee that we're overfitting, but we are likely to be overfitting in that sort of situation. A lot of people used this type of language. I'd say probably at least half the class used this type of language being more equivocating than you should have been at some points. Again, no points off, but try to avoid that habit. Another example, incorrect language. A lot of people said if we are underfitting, we should use a better hypothesis class. And never makes sense to talk about hypothesis classes as being better or worse than another hypothesis class. You can only talk about a certain property of a hypothesis class being better or worse in a particular situation. So you can say that we need a hypothesis class with a higher VC dimension. You could say that we need a hypothesis class with a lower VC dimension. Either of those two things can be better in certain situations. One theorem that we haven't talked about, and we won't talk about in detail, but you will hear people talk about a lot, is the no free lunch theorem. In many areas of computer science, especially areas involving numerical computation like machine learning and data mining, there exist various versions of no free lunch theorems. And for machine learning, the version states that for every hypothesis class, there exists some data distribution that the hypothesis class cannot learn, guaranteed. And so this means that there really is no one hypothesis class that you can always use that's always going to be better than a different hypothesis class. So there's a very jarring mistake when I hear people say something like use the better hypothesis class, or perceptron is always better than stumps. Those are very jarring things for me to hear. Another mistake a lot of people, and this is, I don't know, a more subtle-ish thing. This is not a verbal mistake. This is a written out mistake. A lot of people said DVC equals theta D, and D equals 100 implies the DVC equals theta of 100. And this is something that a lot of people will get very fixated on if you say something like this, and stop listening to whatever you're saying, thinking about that, oh, I just need to correct this person about their asymptotic notation because they must not understand asymptotic notation if they write something like this. Because it is the case that theta of 100 is also theta of 1, or big O of 100, also big O of 1. And so while this is a technically correct statement, it is a not meaningful statement. The better way to describe what people were trying to do when you're plugging numbers into this asymptotic notation to get a sense of approximately how large is something is to say that the DVC would be approximately 100, and not like this. So there is no verbal words that are wrong here that people said this is a written on the board thing wrong. And everybody who did this, your idea was correct. Again, you did not lose points for this, but this is the sort of thing very likely to derail a technical interview and getting the interviewer to be confused about what you do and don't understand. I don't know, any questions about any of the not points stuff before we talk about the points stuff related to the midterm? Okay. Then points stuff. Question, yes. Yeah. So anytime something is just guaranteed to be true, you should not say that it's most likely true. And so the fact that we're overfitting here follows immediately. This is just the definition of overfitting. The in-sample error, and I guess I got my overfitting and underfitting backwards here. I think the in-sample error being greater than the generalization error actually means that we're underfitting. So not most likely because it follows immediately from the definition, but so yeah, just taking that out. I think of this as equivocating language. A lot of students often in the habit of adding qualifiers to what you're saying because it means that if it turns out that you're wrong, you have an out of explaining what you meant. And just making your statements as straightforward as possible, trying to do that, which is admittedly hard in a stressful situation like an exam or an interview, but the sort of habit that you want to be in to make your statements as clear and easy to understand as possible. So again, there are situations where it makes sense to say that you're most likely doing something, but if it just follows from a definition or you're just stating the definition, you don't want to say that kind of thing. Good question. So common ways that points were actually taken off. Probably at least 80% of the points that people missed in the class were from one of these four things right here. The N equals DVC, this is a really big one. Again, this is only a guideline and not a theorem. So if you have to pick an initial place to start, pick an initial hypothesis class, a hypothesis class that satisfies this, and it looks like I forgot the 10 right there, the N equals 10 VC. That's a good place to start, but that is not where you stop. After you've done this, a very common follow-up question that I asked the majority of students was, okay, the new in-sample error generalization error is something else. What do you do then? And the what you do then follows from your new generalization error and in-sample error. This is just a starting point, not an end point. Another common mistake was people saying that if the VC dimension goes down, then that will guarantee that the in-sample error goes down. And this is not a true, what I said out loud is not a true statement. What is written out here is the true statement. That the VC dimension, I got my arrows backwards here, that the VC dimension going up does not guarantee that the in-sample error goes down. The only relationship that we have about the in-sample error guaranteeing relationships between the in-sample errors, this subset relationship. If hypothesis classes are not a subset, then you won't be able to guarantee anything about the in-sample error. Anybody who said something that I had a question about whether you fully understood this or not, I asked a follow-up question comparing two hypothesis classes, usually the circles and the perceptron hypothesis class, finding example situations where the in-sample error of one of those is 0 and the out-of-sample and the in-sample of the other is large and vice versa, and trying to get you to correct a misstatement, something like this. Another common way of missing points, we used the Hoeffding inequality in this class to bound our test error minus our out-of-sample error. And this does not depend on the VC dimension of our hypothesis class at all. Our bound on E-test minus E-out is independent of whatever hypothesis class you use. The reason we can't use the Hoeffding inequality to bound the in-sample error versus the out-of-sample error is that all of our terms that we're summing in the in-sample error are not independent of each other, and the VC dimension is like a measure of how not independent they are. So the VC dimension controls this bound En minus Eout, but the test data points independent of our training data points. So all of the terms being summed in the E sub test are independent of each other, and we can use the Hoeffding, and that does not depend on the VC dimension. If you missed definitely any of these three things on the midterm exam, expect me to ask about it again on the final exam. This last point down here about the universal approximation theorem, a handful of people said that if your VC dimension goes to infinity, that implies your in-sample error going to 0. And the justification for that being the universal approximation theorem. And this is, that is not a correct justification for this. And this statement that I've highlighted right here by itself is not true. An example, a counterexample to that is the convex sets have an infinite VC dimension, but they're not guaranteed to have a 0 in-sample error. So a handful of people, 4 or 5 people mentioned this, and had follow-up questions about the convex sets and whether there was a situation where they would not have a 0 in-sample error. We will see in our notes packet today other universal approximation theorems. The only one that we've seen so far is about the polynomial kernel. And what that states is in the polynomial kernel, as your degree goes to infinity, then combining that together with the perceptron hypothesis class means that the in-sample error will go to 0. But these universal approximation theorems are always specific to one particular hypothesis class and taking some parameter about it to infinity, not about the VC dimension. So pretty much everybody can expect in some way the universal approximation theorem will come up on the final exam, because we're going to see over the next week 2-3 more versions of this universal approximation theorem. So this will be something for everybody for the final exam. These 3 things up here, people who missed these on the midterm definitely see it on the final exam. Any questions about anything about the midterm?
Are you doing the system from last time, like you whiteboard with somebody in get points?
Yeah, that's a good question about getting extra credits back on this midterm. I haven't thought about it yet. So currently, no. I might change my mind on Monday. I will maybe say yes. If a GitHub issue is posted about it, then I will be more likely to think about it and more likely to say yes on Monday. Also, hopefully on Monday, we'll talk about the final exam schedule and get the scheduling for that arranged so that you all can think about your schedule for leaving campus here and going on to whatever you're going to do over break. I was hoping to have that done today, but there's some other things that I still have to work out, so I can't. But by Monday, I'm pretty sure that'll all be worked out. So Monday we'll talk about the scheduling for the final exam as well. Any questions about anything else so far? Okay. Then let's go to the Model Zoo set of notes over here. And maybe a little bit more like background on the Model Zoo before we get into the technical stuff. So where to click first? This Model Zoo set of notes is going over all of the different models implemented in scikit-learn. And so I thought it would be useful and fun change of pace to spend a few minutes talking about the history of scikit-learn and open source machine learning packages. Scikit-learn was the first major open source machine learning package. It was first development started in 2007. Before 2007, there were no machine learning packages in existence for any language. And if you wanted to use logistic regression or neural networks or decision trees, any of these tools, you pretty much had to implement it from scratch. Some of the individual methods had standalone tools, programs for using them, but there was no library, like one library that did everything together. So in 2007, this large group of people right here got together and said, we are going to change that situation, make a one common interface for doing machine learning. And they published their results here in 2011 in this JMLR, Journal of Machine Learning Research. JMLR in 2008 specifically started this track of publications about software packages because it was widely agreed in the machine learning community that we were in a bad place with not having common software that people could use. Vast majority of this software nobody cares about anymore, nobody uses. But scikit-learn here is one of the exceptions to that. Scikit-learn, the reason they did it in Python was because, so they started development in 2007. In 2005 is when NumPy, the package for linear algebra that scikit-learn is based off of, was first developed. And So both of these two software packages, NumPy and scikit-learn, their vast majority of contributors are people who were working on their PhDs, wanted to be professors somewhere, so they started working on all of this stuff during their PhD, and then realized that they can't publish this work anywhere. They can't publish the fact that they have done improving the ecosystem of computer science. And so they ended up dropping out of their PhD programs and going into industry. In this history here, the one thing that I wanted to highlight is that when the project started, the library had little funding and was written mainly by graduate students, and often without a blessing of their advisors. So these were people like basically working in secret from their bosses. Most advisors would have advised against doing things like this. And even today, most advisors would correctly advise their students not to work on software projects like this at all. This is the sort of thing that you don't actually get career credit for. But there's a lot of people who worked on scikit-learn. Here's the pictures of those core developers. Again, all of these people were in PhD programs when they started this development. Most of them forced to drop out of their PhD programs and do something else because of their contributing here to scikit-learn. Okay. One last fun historical note. So Python has a process called the Python Enhancement Process, or PEP, and NumPy had to change a lot of things about how Python worked in order for NumPy and thus scikit-learn to actually work. And so 2006 is when Guido von Rossum, the then benevolent dictator for life of Python, decided that he wanted to actually have Python be a numerical computing language, and he accepted their proposal to change some things about Python to make it suitable for numeric computing. So that brings us to 2011, when all of these models right here were implemented, and what we're going to be talking about today and next week. So last class, we talked about these linear and quadratic models. The summary is that today people only use logistic regression, SGD classifier, or the linear SVC here. None of these other models are actually in use for today. And the real difference about which one you're going to choose, so this logistic regression up here and linear SVC, they're essentially exactly the same. You're not going to find a situation where you get meaningful differences in your output between these two models. It's just a preference that some people have to use one or the other. But logistic regression uses the 2SGD as its default optimizer. So logistic regression or the linear SVC, they are useful for the small data regime. SGD classifier here uses one SGD for its optimizer, and so SGD useful for the big data environment or the computationally limited regime. The SGD, again, becoming popular right around 2011 when this library was being developed. At first, the SGD classifier was not part of scikit-learn here, but it was something that was added because there was so much industry demand for these large-scale tools. The other main thing that I probably touched on, but maybe didn't make super clear, highlighting about these models, is that all these linear classifiers, their DVC is theta of D because they are linear models. They all use the same perceptron hypothesis class. And these quadratic models, the DVC here is theta of D squared because they are using the second degree polynomial kernel before using the perceptron hypothesis class. Okay, so using this knowledge here in red, we can answer these problem 1 and problem 2, or problem 1, part 1 and 2 on the next page. So here, problem one, a colleague is using quadratic discriminant analysis. And here I emphasize that it's a colleague and not you all doing this, because you all know better than using quadratic discriminant analysis. Now, even though you don't know what quadratic discriminant analysis is, probably, the one thing that we did talk about is this does not minimize, the in-sample error. And so you are guaranteed to get better results with high probability if you, instead of using the quadratic discriminant analysis algorithm to optimize the perceptron hypothesis class in polynomial degree 2, you use logistic regression. Logistic regression actually minimizes, EN, and so you'll get better results. The statistical properties, the generalization error, the same between these two hypothesis classes, but one directly minimizing EN, the other not. And so the one that minimizes the in-sample error will get you the better results. So a colleague is using quadratic discriminant analysis to solve a machine learning problem and provide simple suggestions on how they could improve accuracy, classification accuracy in the following situations. Situation one is they are overfitting. And so that means that our in-sample error, again, in-sample error, low compared to generalization error. And so the solution here is the same sort of solutions that we talked about on the midterm exam that you're starting. So the quadratic discriminant analysis, QDA is a common abbreviation for quadratic discriminant analysis. The Q for quadratic, DA for discriminant analysis. QDA is the H perceptron with polynomial degree 2 feature map. Hypothesis class, that's the hypothesis class that it uses. And so any tool that we had previously for talking about the perceptron model with this second degree polynomial class and how to prevent overfitting, we can apply to quadratic discriminant analysis. So I'll just write 2 examples here. We could come up with more though. So example 1, example solutions are first apply a feature reduction method. To reduce our features down and prevent the overfitting. Or the second is change our polynomial degree to a smaller number. Change, so the Q from the polynomial degree to 1 instead of 2. And that's equivalent to just removing our polynomial feature map. So if you really, really wanted to stay with discriminant analysis for whatever reason, which you probably don't, I know of no good situations where that would be the thing to do. There is a linear discriminant analysis that is implemented in scikit-learn that you could use. So LDA for linear discriminant analysis. That is one of the hypothesis classes up here. Linear discriminant analysis. You could use that. But probably better, again, almost always better just to use the standard logistic regression or SVM. And this reduces our VC dimension, so it reduces our generalization error and solves the overfitting problem there for us. The key difference, the only difference about this problem right here and the previous problems that we talked about for the midterm 2 is that now I just said quadratic discriminant analysis, and you have to infer from that what the hypothesis class is. And but once you've done that inference, then all the other reasoning is the same. Any questions about that? Okay, the opposite here, in part 2, the training error E sub n is large. Then we could do the whatever techniques we had before for preventing underfitting. For midterm 2, or we can switch to a model that actually minimizes the in-sample error. Switch to a model. Again, a model is a hypothesis class plus an algorithm for learning and a hypothesis in that hypothesis class. So switch to a model means change the algorithm that minimizes E sub n, which would be logistic regression with the poly feature map of degree 2. For any possible question that I could ask about anything in scikit-learn related to the linear quadratic hypotheses that we talked about above, they're all going to relate to the stuff that we talked about from midterm 2 somehow. So as a more meta comment too, one of the things that I'm not going to ask you to do as a programming assignment is to actually implement or solve some data set with any of these algorithms that we're talking about in the model zoo. It's not hard to do. I have confidence that you all would be able to do it, but I've just decided not to make you all do it to reduce your all's workload for this class. So if it's something that you're interested in, it's worth doing it. Just picking some data set and picking one of these algorithms and tuning the hyperparameters for all the things that we've walked through at a high level in class, but I'm not going to make you sit down and actually do it. The documentation for scikit-learn is very good. It has a reputation for being some of the best documentation of any software package. It walks through a lot of the machine learning stuff as it relates to code. And so just reading through the documentation, finding some spot where it does that is a good thing to do if you want more programming experience related to data mining. Okay, but what we're going to talk about next is our multi-layer perceptron here. And the multi-layer perceptron is one of the simplest neural networks. All the theory stuff that we'll talk about in this notes packet is stuff that we will see about the practice of how to do that in PyTorch in the next homework, in the homework that is in the next PDF file, in the next notes packets. These multi-layer perceptrons were among the earliest models, earliest hypothesis classes to be thought about in the machine learning community. So they date back to the 1960s. And today, in scikit-learn, not widely used in scikit-learn because PyTorch and TensorFlow have largely replaced scikit-learn for this. Both of those two libraries coming out in 2015, and they remain the state-of-the-art way of talking about neural networks. But so here, the multi-layer perceptron, what is it? So here is our hypothesis class of half spaces, or the perceptron hypothesis class. Those are two synonyms for the same mathematical object right here. And we've already talked about that it's very common to adjust your VC dimension by applying some sort of feature map. So everything here in this first paragraph is all just like review from stuff that we've talked about before, just reminding ourselves of the notation here. The key idea of the multi-layer perceptron, though, is that if we are machine learning people and serious about learning things from data, then why should we hard code one of these phi functions and not just also learn the phi function from data? And so that is the idea of the multi-layer perceptron. This equation 3 right here is the key formula for the multi-layer perceptron, that we are creating some new feature map, some new phi of x, and it's parameterized by this W1 here. This is sometimes called the weight matrix. And now not only are we learning this W from the hypothesis class up here, we're also learning this W1 from this phi function down here. This sigma function right here called the activation function. It has a handful of different names in like way back in history, but everybody today calls it the activation function. Maybe the one other term that you might hear it sometimes referred to as, you might sometimes see the activation function, the sigma there, referred to as the nonlinearity. A one-layer neural network only has, or a one-layer multi-layer perceptron only has one version of this phi function like this with one weight matrix. But a multi-layer perceptron will repeat this idea many times, saying, okay, now we have another x variable. Maybe we want to do a feature map on this new x variable that's inside this feature map. And so some recursive application of this phi function is how you get a multi-layer perceptron. So equation 3 right here is one layer. One layer. And down here, this is the multi-layer. I've got a web page that we're going to go visit to next and play around with some of these parameters and visualize what's going on in this multi-layer perceptron. Will be important that you're familiar with this syntax and notation down here, able to reproduce this syntax for the final exam. And these next set of notes down here are a lot of theoretical results about multi-layer perceptrons that will require you to have this notation up here above memorized in order for the theory to make sense. But what we're going to next is this link right here, and talking about some of the intuition behind these multi-layer perceptrons and how they fit into the ecosystem that we've been talking about so far. So this is a link to the TensorFlow documentation. I have that opened up right here. So in this, okay, I don't know how to move that. In this picture, in this web page, what we have going on is on the right-hand side over here, we have a data set like we've been visualizing before. They have two classes in this data set, the blue class and the orange class. And our goal is to learn some sort of model that is going to predict between these two classes. In this case, there's a relatively easy problem to predict. The true data without noise looks something like this. It's basically two Gaussian distributions for our data over here. And this noise slider over here, adding noise until the classes slightly overlap each other. So the Bayes error in this case will be non-zero, it will be above 0. But we'll still be able to get good classification performance on this problem. If I press the play button up here, it will run the optimization for us. It's using stochastic gradient descent for the optimization. We can do things like change around the learning rate up here, and you can see that it doesn't really have too much of an effect. If we make the learning rate too large, you saw how it wiggled around like that for a bit. That's the instability that we were talking about from the too large learning rates. They don't let us make it so large that it gets a divergent behavior, but if you change the learning rate to 10, you'll very often get that a little bit of instability before it settles off again. So this is an easy problem right here, even if we add some noise. A more difficult problem, this circles type problem like this. And if we are learning a perceptron hypothesis class, again, like we've talked about, we can't actually learn this, this model here. So here you saw with my learning rate of 10 there, it was bouncing around a lot until it's finally settled down to something smaller. And this is like the best that we can do with our perceptron hypothesis class, and it's not a very good result. If we add a feature map though, so these right now, there's two-dimensional, the only features it's using, this x1 and x2. We add these other features like this, the quadratic feature map. This x1,2 is like the x1 squared value, x2,2, x2 squared, x1, x2, x1 times x2. So adding these 3 points right here, these 3 additional features, this gives us a quadratic feature map and allows us to actually make these circles like we've seen before. And we don't get down to 0 error because there is this noise. But the point here is that this is that polynomial feature map that we're familiar with now. And there are other data sets like this XOR data set. So this has the blue in the top right and bottom left corners and orange in the top left and bottom right corners. And the polynomial feature map also able to do really well on this data set right here. It is said that the polynomial feature map, though, is not able to do well on is this spiral-looking data set. So you can see there's the orange and the blue sitting together in this spiral sort of shape. And if we run the model like this, it's going to bounce around a lot, eventually converging on some sort of maybe I don't know, the best solution that it can get, but it's not a great solution right here. And so one thing that we could try to do is we could try to come up with like manually program a feature map that's going to unravel the spiral for us in a high dimensional space. And if we know the data distribution somehow, like in this case, we would know it, it is a reasonable task to come up with this phi function for us analytically. But in general, we don't know like what this data distribution is going to look like. And in very high dimensions, like machine learning problems, often in the billions of dimensions, it's very difficult to visualize and have any hope of guessing what that best feature map could be. And so that's where the neural networks come in, is to try to learn that feature map from the data for us. And so on this website here, I can add, there's currently 0 hidden layers. So a multi-layer perceptron with 0 layers is equivalent to logistic regression. Now, if I add 1 hidden layer, this hidden layer up here is going to be learning a feature map for us. So I'll take away this feature map right here, and then we'll see how good we can learn on this data. At this point, it's not doing great on this data set right here. We'll see in a little bit that you need a much more complicated internal feature map to be able to learn this spiral shape. But if we go back to these shapes that we do know about, like over here, try this. Okay, now we're getting a little bit, I don't know, some sort of interesting thing is happening here. It's still not great though. We're not getting perfect results. But if I add more layers into this, make this individual layer right here wider, then I will be able to fit this data. You can see that it's not getting a perfect circle over here, but it is approximating a circle reasonably well. Each of these straight lines over here, it's like an edge of a polygon. Each one of these internal hidden layer features is defining one of those lines. As I add more of these hidden layers, the polygon approaches more of a circle, and as I take away some of those hidden layers, the polygon is less and less circle-like. Question?
Yeah, so does are we learning the sigma function?
Question is, what exactly are we learning here? And the answer is in the notation over here, it's these W matrices that are the parameters that are being learned. The sigma function is something that is fixed in advance. In this website over here, there's this activation. Right here, it's a little bit, there we go, the activation. Here we can select the 4 different common activations to use. The The ReLU is the most common one these days, or the TNH or sigmoid or linear. And one of the things that we will talk about here in a little bit, theoretically, is that this linear activation function can't do anything beyond what a standard logistic regression does. No matter how many hidden layers I have, and no matter how big these hidden layers are, the linear activation function will be equivalent to logistic regression. The most common activation function to use these days for most tasks is this ReLU activation function. ReLU is equivalent to the hinge loss. So it's equivalent to doing an SVM at each individual step right here to learn this inside parameter. And it's common for being efficient to compute. The only situation where ReLU is not commonly used these days is in reinforcement learning. If you're doing something related to games, it turns out that the TNH or sigmoid works better in those situations. But on a data set like this, the sigmoid, TNH, ReLU basically always have the same performance, but ReLU is a little bit faster, so ReLU has become the popular thing. This is again, a hyperparameter, something that the user chooses in advance, and it's the W matrix over here that's the thing being learned. The W vector and these W matrices all learned in conjunction with each other.
So when we didn't have anything later, we said it was basically the same thing. But because we put slightly like x12 and x22 and x1, x2, isn't that automatically we get to that we have a prime feature map and therefore we have some W prime matrix?
So with the x1, x2, these additional features right here, these are a new feature map, but these are not a learned feature map. These are a feature map that it's the polynomial of degree 2 feature map. And the polynomial of degree 2 feature map, it changes the dimension of our x data points that are getting passed into the hypothesis class. And so it does change the dimension of W, does increase the number of parameters that we are learning, but it only increases the number of parameters in this W vector that's directly inside the hypothesis class here. There is no learning of the feature map itself. When I select these three elements down here, there is no learning of the feature map. It's like hard coding the feature map. So there's no W inside the feature map that's being learned. It's the polynomial feature map in that case, and not the multi-layer perceptron feature map. When I add a hidden layer right here, this is not a hard-coded feature map. This is one that we're going to be learning from the data. And this individual hidden layer right here corresponds to this phi function right here with the W to be learned.
So if we have 5 neurons in the like phi of, or if we have 4, would that be the maximum phi of x1? Because we only have x1 and x2. If you go back to the website, it means like blue lines of where there's a neuron, where there's a x1 and x2 leading into it. Is that x1 and x2 then?
These have no relation to x1 and x2. For this particular problem, we might hope that this right here would approximate the polynomial degree feature 2 feature map, but there's no direct relationship between them. Yeah. Good.
Rena left a question in the chat.
I can't get to it. Can you read it to me?
Log on. So you read it?
Here, I can tell you.
Go ahead.
What is the difference between increasing the neurons in the hidden layer versus adding another hidden layer?
Question is difference between increasing the neurons in the hidden layer versus adding a hidden layer. And so over here, when I add the hidden layers, more hidden layers, syntactically, the way that comes up is there's more recursion happening down here. This superscript I over here is the number of layers that we're doing recursively. When I am adding more neurons in that layer, it's changing the dimensions of this W matrix right here. Each of these W matrices has an input shape and an output shape. The output size is the number of neurons in that particular layer. Yeah, the main, again, yeah, the main thing to take away from this visualization is that the stuff in the middle here all learned, and so we can have the same shape of our neural network learning something, and if it's in a different data set, the hope is that it will learn about that particular data set and get the be able to fit that particular data set without us having to manually specify what the features are. The interesting case for that is in this spiral situation right here. We don't know a feature map that can get this spiral situation accurately map that into a high dimensional space. But it's reasonable to learn that with a neural network. We can see what sort of shapes are going to be coming out here. That this decision boundary is slowly getting more and more like the neural network. If we make this a little bit more complicated, it's more likely to be able to get that shape. In the top right over here, this graph is a graph that we haven't talked about too much. On the x-axis here is time, and the y-axis here is our training and test losses. And so you can see that as time goes on, the training and test losses are going down. You can see that we're in a bunch of instability, a point of instability right now, that the decision boundary is changing a lot on each step. This tells me that the learning rate is likely to be too large at this point, that we're diverging a little bit. And if I lower the learning rate, so it starts at 0.1 here, go to 0.01, things stabilize off again and start getting better. If I make my learning rate too large at this point, then we will suddenly get really, really bad all of a sudden doing that divergent behavior. So the takeaway here is that this complicated internal structure can get us a, reset that, rerun that, can potentially learn complex functions for us that we don't know how to analytically describe. Yeah, if things are being unstable somehow, it probably means your learning rate is too large, and decreasing it likely to help. Yeah, let's see. Nothing else that I want to talk about this picture or this webpage. It's worth playing around with it some more on your own, but yeah, go ahead.
Yeah, more things. Are you just like continuing to left multiply this like vector with another W?
So adding more hidden layers means unraveling this recursion right here, which yes is adding more W matrices that you are multiplying together. Each one having this sigma in between them that's that activation function, so that it's not a purely linear function. It has some sort of non-linearity in between all of those matrix multiplications. So the next page down here talks a lot about the theoretical results about machine learning of multilayer perceptrons, which I think will start to be answering a lot of the questions that it sounds like you all are asking about, essentially why to do certain things, why to add more layers, why to add more, change the size of the layers, how do you decide what these different hyperparameters should or shouldn't be. And again, these theoretical results will get us towards that direction, helping us out a little bit. So the first of these results here, theorem 1, is a universal approximation theorem for neural networks. And so here, let G be the ERM hypothesis, so the minimizer of the in-sample error for the one layer MLP hypothesis class, so only one hidden layer. And our D1 value right here, this is the size, the number of neurons in that hidden layer, D1 number neurons in the hidden layer. As that grows to infinity, then our in-sample error guaranteed to go down to 0. So this is one of the first celebrated results of machine learning. It dates back to the early 1980s. And the high-level intuition of this, the English version of this theorem right here, is that the MLP with one layer can learn any function. And so back in the 1980s, people were very excited about multi-layer perceptrons for this reason, because with just one layer, it turns out that you can learn any possible function that you might want to learn. Like the polynomial feature map that also had this universal approximation theorem, there is the risk of overfitting, though. And so the majority of this page talks about the overfitting situation, and in particular talking about the VC dimension of our multi-layer perceptrons. There's going to be two key quantities, this E quantity and the V quantity, that are commonly defined in order to talk about the VC dimension. Here, all of these D's in this equation right here come from the shape of our W matrices. And so again, each W matrix has some D sub I that is part of its shape. And if you follow these equations, the meaning of this E equation is that it is the total number of parameters in all of those W matrices added together. Total number of parameters in all W matrices added together. The E here stands for edges. And so it's common to draw these, or was back in the 1980s, common to draw these neural networks as like a graph shape. Not so common anymore, but that's where the E letter comes from, is it comes from edges. But what it really is it's the total number of parameters in all your matrices. This is so we have K of these matrices in a K layer multi-layer perceptron, and we're just multiplying all of those dimensions together in order to get the total number of parameters. This V value here, this comes, so the V stands for vertices. And it's the total number of neurons in each layer multiplied together. So each one of these D sub i's right here, if I go back to the web page, here the first D sub 1 would be 5, then D sub 2 would be 4, then D sub 3 would be 4. It's the total number of these neurons multiplied together. It stands for vertices. That's the semantic thing of what it is. If I scroll down to, or scroll up to the previous page here, this hidden layer size parameter in the multi-layer perceptron classifier is a list of all of these D values that you're passing into the model. So it's a list of, say, D1, D2, D3 in a 3-layer multi-layer perceptron. And so this hidden layer size variable right here is the hyperparameter to the MLP classifier that determines for us what our E and V variables down here, what they're going to end up being equal to. There's no way in the code to manually specify the E and the V values. Instead, you specify these D sub I values by specifying in this list right here the hidden layer size. From that information, we can calculate the VC dimension in depending on the activation function. And depending on which activation function you use, you'll have a different VC dimension. So one of the standard results is that if you use the identity activation function on the website, this was called the linear activation function. Then the VC dimension is just the VC dimension of the perceptron hypothesis class. And so there's no additional power you get from a multi-layer perceptron if you're using the identity activation function. Because of this, it is never used in practice and only used for explaining toy examples. We have a handful of other bounds on the VC dimension too. And in general, it is an open problem about what the exact VC dimension is of any neural network. It's something that we don't know how to compute. Nobody knows how to compute. We just have a series of bounds. And so the best bound that we have on the K-layer multi-layer perceptron with the sign activation function, this one is not in the web page at all. This is also never used in practice because, again, it's impossible to optimize. The sign activation function here, again, being the 0-1 activation function that we've called it before, not used in practice because it's hard to optimize. And the VC dimension of this sign activation function is essentially the number of parameters of our multi-layer perceptron. It's essentially how many of these individual numbers are in all of these W matrices together. Because again, E is the number of parameters that we have, and our bound that we have is E log E. So the big picture idea here is this is basically the number of parameters. Often when people talk about the complexity of multi-layer perceptrons or neural networks in general, they talk about the number of parameters in that hypothesis class. And the motivation for that is because if you use this sign activation function, then the VC dimension is essentially the number of parameters. In practice, though, again, nobody uses the sign activation function and nobody uses the identity activation function. The TANH activation function here, again, very popular in these days reinforcement learning settings, which is like playing games. And in this case, what we know are these two bounds right here. We don't know anything in between these two bounds. We know that the VC dimension must be at least E squared, and at most V squared times E squared. But notice that this is much, much higher than the number of parameters. This is the number of parameters squared. So much higher than the number of parameters. So the number of parameters by itself, if you're using the TANH activation function, is not your VC dimension. It's actually the square root of your VC dimension. The VC dimension grows much, much faster than the number of parameters here. Again, open question whether that is tight or whether you need this additional V squared factor in front. Throughout this set of notes, there's a handful of references right here. You're not required to look through these references at all. They're mostly bookkeeping for myself to make sure that I'm not telling you anything that's untrue. But if you were curious about where this bound is located, it's there's the citation for it for the actual proof. I'll pause here for questions in a little bit, but let's keep going for now. Theorem 3, so the ReLU loss, or the ReLU activation function. This is the most commonly used one in practice. One of the reasons for that is computational, that it's very fast to compute. But another reason is that the VC dimension bound over here is much, much smaller than the VC dimension bound that we had on the tan H. So here, notice that we are linear in E, which is significantly better than quadratic in E. This K value right here, this is the number of layers that you have. And so for a one-layer multi-layer perceptron in particular, then just the number of parameters is a good sense of how big your VC dimension is. One of the things about deep learning, so the deep learning revolution, again, happening around the 2014, 2015 time when the PyTorch library, TensorFlow coming around. Deep learning has K set to be very large values. So one of the ideas of deep learning is K is very large. Typical values, about 100. And so this is making your VC dimension much larger. So having even more powerful, more complex models. K is the total number of layers in our multi-layer perceptron. And so going back to our the MLP classifier in scikit-learn, the length of this list is equal to K. So in this case, K would be equal to 3. So one of the important takeaways here is that the complexity of your model is very much going to depend on this hidden layer size, whatever you pass into the MLP classifier over here. But it's also going to depend on the activation that you pass into this MLP classifier. Both hidden layer size and activation will affect the VC dimension. These two together will determine the DVC. The solver and the alpha independent of DVC. No effect on DVC. The solver is the optimization algorithm that you can choose to use. And there's 3 choices. LGBFS is one method for 2 gradient descent, and then one called SGD, which is just the 1 SGD standard, and then one called Atom, which is a 1 SGD variant. In practice, nobody uses LGBFS. Nobody uses 2GD for neural networks in any situation. People only use SGD or Atom. SGD here being the default. Many reasons for that. One is statistical, that for if you're using multi-layer perceptron, then the assumption is that the computation here is very difficult computation, and so you're going to be computationally limited. So people only use these. People only use these. One reason is MLP computationally expensive. The other reason is that it turns out for these multi-layer perceptrons that SGD and Atom more likely to get you better optimizations. So more likely to get closer to the global minimum. They get better minima. I'm going to scroll down here in a second to illustrate why that is. It's related to this fact right here, that these, when you chain these multiplications together with these non-linearities in between them, like you're doing right here inside of this phi function, This makes the optimization very, very non-convex. And so in one dimension, your loss function is going to be very crazy looking with lots and lots of squiggles like this. This is a typical E-in value for these multi-layer perceptrons, having lots and lots of squiggles. And stochastic gradient descent, one of the turns out that the stochasticness here is really beneficial because you're randomly moving, you randomly are able to get up and out of these local minima and get closer to the global minima. But if you're using a standard gradient descent likely to get trapped in one of these local minima. So, and in particular 2GD, the LGBFS, likely to get trapped in local minima, but SGD or Atom, one SGD, Atom again being a variant of that, can, because there's inherent randomness, you're going to bounce out of these local minima and not get stuck somewhere up at the top. Likely to bounce out of a local minima due to randomness. This is a very, very high-level overview of these choices of optimization. We still don't have a good theoretical understanding of why SGD or Atom are able to, in practice, optimize these deep networks, these multi-layer perceptrons. We don't understand very well exactly what this non-convex shape looks like. But this is one of the stories that people like to tell, is that, again, without randomness, you're likely to get stuck inside of a local minima. But if you have randomness about where you move, then that's going to take you out of a local minima, and you might not find the best one, but you'll get at least closer to a global minima. For the final exam, and we'll be having a quiz here in a week or two. You'll need to essentially have all of these formulae here memorized so that you can tell me about, like, okay, if we are, and we'll talk about these questions next time, but with these different shapes of our network, with these different values of hidden layer size and activation, are we more or less likely to be overfitting our data? Do we want a network that looks like this, 10, 10, 10, or a network that's like just 100 by itself? And in order to be able to answer this, you'll need to have all of this information up here memorized. That's a good stopping point for us today, though. Again, you have this, this next notes. We'll talk about it in detail next time in class, but you have enough knowledge now to at least start this notes and take a look at the PyTorch documentation here. But we'll talk more at a high level theoretic knowledge about the homework here next time in class.
I'm not a dumb question, but I don't understand how like a tan H function is applied to